system green. I don't really know that many juniors. I knew what I meant. I wasn't confused. Oh, would you like paper? Okay, I just want you to be happy. Oh, you are the right person to ask, Luke. I disagree.
I'll do anything chemistry related. Biology, maybe.
How many of us know what the products are? Okay.
I'm not one of them.
Close?
Close.
Not quite.
So if we listen to Luke's idea but not his words, Luke says that the products are going to be the alcohol and bromide. You just simplified the alcohol too much. You made it methanol instead of as complicated as
Sorry.
they were before. That's what I'm saying. Like the spirit was good, but the word wasn't good. Is that fine? So this is nucleophilic substitution. That means that this nucleophile, again, positive charge loving thing, is going to replace that positive charge loving thing. And so we're going to do the arrows. Now you might recall that SN1 is a two-step process. In the first step, we actually don't even use the nucleophile. In the first step, what happens is we break this bond. So we're going to draw an arrow from the sigma bond between carbon and bromine toward the bromine. And this is an example of heterolytic cleavage. DT and I were sharing a bond, but she's now going to take both of the electrons. I'm going to get none. So it's different. She took 2, I took 0. Heterolytic, different breaking. So free radical substitution, homolytic. Only example we have of homolytic. Only one where we have radicals and crazy unpaired electrons. Everything else, 2 electrons are moving around. Everything else is heterolytic. We only have to draw arrows for heterolytic things. The other ones are optional, a nice place to practice and think about it. These are mandatory. So the products, again, are me losing my electron and becoming positively charged carbocation intermediate. And a DT, my leaving group, giving off that bromide. In the second step, the nucleophile finally comes along. And what is it going to make? My God. It's going to make a new bond, a coordinate covalent bond. Why is it coordinate covalent, Mohab?
Takes both.
Just 2 2 electrons are coming from one source. And as Luke said, we're gonna end up with the alcohol. And as my girl Karthika knows from last class, Margaret knows I'm trying to get every mark. I'm gonna put that bromide down just to make it easy on the examiner. Bueno. One more time, the marks associated with this pretty blue arrow, the right carbocation intermediate, this pretty blue arrow, and the correct products, 4 marks. Is this a primary, secondary, or tertiary haloalkane? Tertiary. That's right, because the carbon that's attached to the bromine has 1, 2, 3 carbons attached to it. SN1 is a 2-step, and it's best for tertiary haloalkanes. The reason that it's best is because we want to stabilize this carbocation intermediate. It doesn't look very happy to me. I don't know how it looks to you, but like the whole idea of this reaction is that I've got this really nice molecule sitting in some sodium hydroxide, and like spontaneously it's like, you know what, I'm just gonna get rid of this bromine. Like I just am not feeling it. Like that's weird. I would not expect that reaction to occur. It does actually occur quite quickly, and that's because of 2 things. The first one is that this product is relatively stable. Now you can see that this carbon is missing an electron in the structure that I drew you. Is that fair? But you also see that there are 3 carbons bonded to it. What do you think might happen if you guys had a friend who was missing lots of money because they had bought me a very handsome gift? What might you do? You would chip in. You would try to offset that. And what we find is that the alkyl groups that are attached to that positive carbon funnel electron density into the carbon. That is referred to as the positive inductive effect.
Wait, they funnel what?
Electron density. So they see a carbon is missing electrons. Instead of having 1 carbon missing a whole electron, the carbons will push a little electron density over so that all of the carbons are a little bit positive instead of having 1 that's all the way positive. So instead of having 1 person give up all of the money, everyone's gonna chip in and be missing a little bit of money. The carbons that are attached, the alkyl groups that are attached to the positive carbon will feed electron density into that positive carbon, kind of distributing the positive. You can't distribute positive charge, you can only distribute electrons, but like in your brain, you can think about it that way. We're distributing the missing money. Similarly, you can't distribute missing money, you can only distribute money.
Well, you're breaking the law, you can distribute missing money.
If you like to look at mark schemes because you're that kid, sometimes you'll see positive inductive effect written as a positive sign and IE. To me, that looks like ionization energy. It's very confusing. It's just in a mark scheme that way on occasion. Like you'll just see that as a shorthand. And so I want you to know what it might mean. I'm not gonna try to use that shorthand, but if you read it and you're thinking ionization energy and you're like, why did she never say this in class? It's because it's the positive inductive effect. And again, it's when you have alkyl chains push electron density onto the positive carbon to stabilize it. It's a little bit like resonance, right? It's talk or bad talk? We okay? Talk talk.
Is the ferroelectric fusion that happens in
Yes. This will actually happen in water. When we do it in water as the solvent, sometimes you'll see it referred to as solvolysis. Solvo meaning the solvent is breaking that bond. Solvolysis. Solvolysis.
There's like heat effect.
I assume it makes it go faster. I assume. If we had to draw the reaction profile for this, because y'all are talking about kinetics, this is a two-step process. You told me the first step was likely the slow step. So you would have reactants.
Isn't the first step the spontaneous?
What is this?
breaking?
Overall reaction is
Reaction
spontaneous.
profile.
It happens without me doing anything. So it's like saying, is the water that's not in this cup evaporating right now? It is not a spontaneous process right now, but some of the molecules of water in the cup are on the high end of my Maxwell-Boltzmann distribution curve, and they have enough energy to escape. So some of these molecules have enough energy to overcome this step. It is, not looking very spontaneous, but because the second step is spontaneous, it can couple and it will stay over here. The x-axis here is known as the reaction coordinate. The y-axis we typically call energy. And I've shown you the reaction, the intermediate, and the product. And we're saying that this activation energy is much bigger than this activation energy, so that first step was the slow step. Or the rate determining step, I like that. That's why we argue that this reaction could be called SN1, because it was unimolecular, or the overall order of the reaction was 1, because there was only one reactant.
So the rate of decay and the concentration
Yes.
of it.
So Emma just said that the rate would be equal to the concentration of this raised to the first power. Again, that's why we call it SN1. So now I'm going to draw the other nucleophilic substitution. So now we're going to do something new. 1971. I assume it was a code for something in Canvas. I don't know what you see. Okay, unsurprisingly, this is going to be called SN2. S still stands for substitution, N still stands for nucleophilic, but 2 is going to stand for bimolecular, or second order. You guys already know what the products are going to be. We're going to substitute that bromine with the hydroxyl and make ethanol and bromide. But it's going to occur differently. While the process over here is 2 steps, we'll sometimes refer to it as sequential. The process over here is going to occur in 1 step, and so I'm going to use a different word. I'm going to refer to this one as concerted. 2 things happening at the same time. So in a dark way, if you have that friend who doesn't want to ever be single, they're breaking up with one human as they are attaching to the other human, that is this process. You've met that person. I don't know who it is, but you've met them.
There is definitely another.
I have a carbon-bromine bond. Could you guys comment on the relative electronegativities of carbon and bromine? It's an halogen, Raimi. Okay, so bromine is more electronegative than carbon, so this bond is polar, and the carbon is going to have a partially positive charge, while the bromine is going to have a partially negative charge. So if this hydroxide nucleophile were to come in, where would it like to be? On that carbon that's positively charged. So we're going to draw an arrow from the lone pair on the hydroxide to the carbon. this is concerted, what's gonna happen is the bond between carbon and bromine is gonna break. So we're doing two steps at once. Instead of first the CBr bond breaks, then the hydroxide comes in, now what's happening is as the hydroxide comes in, the CBr bond breaks. Concerted at the same time. And so here, what we do is we draw the intermediate. Can someone, oh shit. We draw the transition state. Can someone tell me the difference between transition state and intermediate? It was a really hard question. Can you tell me the difference between intermediate and intermediate? Like, ooh, we used the wrong word. What you got?
The intermediate is like a different product made, and the transition state is just what's there between the steps actually happening.
Okay, so try to bring that home a little bit. This is that same reaction coordinate picture that we're drawing. This is the transition state. Y'all might call it the activated complex in another class. We're talking about the highest energy thing. It is not a local minimum, it is in fact the global maximum. Doing derivatives in another class, Audrey, it's a party. Isn't it fun?
So meant to stand now.
So like when the arrange bonds receives, and at the same time the beams break.
And so we draw that. And so what we're gonna do is we're gonna draw the 5-member transition state. So I'm gonna put a carbon in the center. I'm gonna erase my reaction profile. I think it's really a good one, but I'm gonna erase
So
it.
what's the intermediate state? There's no other second reaction.
Okay, so I have drawn this carbon. It is attached to 2 H's and a methyl. And I'm gonna show the bromine bond breaking. And I'm gonna show the hydroxide bond forming. And I'm gonna show in 2 ways that this is a transition state. There are 2 notations that denote transition state. One is placing the whole thing in square brackets, and the other is this cute little thing called a double dagger. Double dagger. I also must show that this transition state has a negative charge. If you look at the total charge on the left-hand side, do you see it adds up to -1?
Where?
That means that the total charge on the right side has to add up to -1. So it's just a way of reminding yourself. So there are 3 things I have to see in this picture to give it the mark. Thing number 1 I have to see is dotted bonds. If you draw a carbon with 5 bonds, I can't give you the mark. Number 2, I have to see a negative sign. And number 3, I have to see that it's a transition state.
What was number 1?
Number 1, I have to see dotted bonds. This arrow is optional, but I like it. It's the same arrow I drew here, and I'm just reinforcing the fact that that bromide is finally gonna leave. And we are gonna make H3CCH2OH and bromide. So one more time, this is 4 marks. Mark number 1, hydroxide to the carbon. Mark number 2, CBr bond to the bromine, 2 curly arrows. Mark number 3, the transition state correctly drawn with dotted bonds, a minus charge, and it's clearly a transition state. And mark number 4, the correct products.
We need brackets and the double.
You need brackets. I grew up with a double dagger. I will often just write those. It's like a little party of symbology there. On the center board, I told you that the SN1 reaction could take place because the carbocation intermediate was pretty stabilized by this positive inductive effect. Instead of one carbon losing a full electron, all the carbons kind of pitch in and make it not so hard on that singular carbon. Here there's another thing that's trying to help make sense. Would you describe carbon as a big atom or a small atom given its placement on the periodic table? It's very small, right? There are like 6 at most atoms that are smaller than carbon, right? It's tiny. And what I'm asking carbon to do is not just make 4 bonds, but make 1, 2, 3, 4, 5 things around it. And that's a lot for something that's really small. And so the only way that I can really make that happen effectively is if I make sure that the carbon has some really, really small groups on it. So instead of having something bulky like an alkyl chain, if I can have something tiny like hydrogen, it might be possible to fit all 5 of these things in bonding distance to that super tiny carbon. And so this is preferred for primary haloalkanes.
The SN2?
Yes, because they have the least steric hindrance. If I were a better person and didn't sit in on a math class instead of studying, I could perhaps have looked up what steric meant. But since you guys are largely biologists, I would like you to consider for a moment non-competitive inhibition. Can you picture that?
Yeah.
We have an allosteric site. So what does steric mean when you say allosteric site? Okay, I tried to give you something that would tell me what steric
We
meant.
probably wrote it down last year sometime.
Steric means something about the size and shape. It means how much room is available. So the allosteric site, my understanding of what it does is that it changes the shape of the active site. So the allosteric site is going to change the shape, and so we're saying that there is no shape-based hindrance. There is enough room for all of these things to fit. So again, while I didn't look up the word to me has something to do with 3-dimensional things fitting together, right?
So, if like the carbon had like a very long chain of carbon like is it gonna like push it and make it harder?
Ultimately, yeah. Like we would like this to be as small as possible. So the fastest SN2 reaction would happen with methyl. Then we're going to choose a primary, and chain length is probably going to be inversely related to efficacy. And then we're going to choose a secondary, and then last we would choose a tertiary. Yes,
So you mean whatever is attached has to be small,
yes.
not like the thing itself?
So I'm most worried about like the atoms that are right here. So these 5 atoms are my biggest concern. And so my biggest concern is, are these hydrogens or carbons? So given the choice, I want them all to be hydrogens, so that would be methyl. Given the next choice, I'm gonna have one of them be a carbon. But Audrey's saying that if one of them were a carbon, she thinks that there could be an effect to what that carbon was attached to. I mean, you have to be right.
Because I looked it up and then it talked about how shape and the smaller
That is like a different case of joy that you're kind of reading about. So what she's reading about would speak more to, she has a picture of cyclobutadiene. And what kind of steric effects might this have? My guess that this reaction is going to, or this molecule is going to be quite reactive because I'm forcing this to take on a shape it doesn't want to. This wants to have 120 degree angles, and I'm forcing it to have 90 degree angles. Imagine if instead I did this to cyclopropene, and this is wanting to have 109.5 or 120 degree angles, and I'm forcing it to have 60 degree angles. This is very bad, this is pretty bad, and if I can get it all the way up to cyclohexane, it's probably gonna be just about okay. That's what I looked at on our phone, but if we read the full article, maybe we know more.
So do those ones have a halogen on them?
Yeah.
Like the fuel is.
Yeah, they could. But they also have, like, they both had double bonds in them, so they would have other chemistry available to them as well. Okay, SN1, SN2. So the point that you guys helped me to make is that SN1 prefers tertiary because it's stabilized by the positive conductive effect. Remember saying that? Still circled on the board. That guy, the positive. So let's try doing SN1 with something that's primary. Let's try chloropropane. Can you draw the SN1 mechanism for that?
What is this?
You are drawing the SN1 mechanism for chloropropane. You've been very quiet today, Sophia.
Okay. Melania's not here.
My favorite nucleophile is hydroxide. It's the only one I can 100% guarantee that you have to know. On occasion, you can throw down another nucleophile. I don't know that we need to do it today. Cyanide is fun, ammonia is fun, water's okay. Some of them come with some new problems, but I just wanted you to try draw it, so I'm just really stalling for you to draw a carbocation intermediate, 2 arrows, and the products. So we're gonna make the nucleophile hydroxide because it's enough, right? I'll be right back. Okay, so everyone's looked quite good.
Well,
You showed me the chloride leaving, making the carbocation. And so let's take a look at this carbocation. Is it stabilized by the positive inductive effect? In a limited way. It only has one ethyl chain that's able to help out. And so this is not very stabilized by the positive inductive effect. So if we wanted to compare the reaction profiles, we have the reactants, we have the intermediate, and we have the products. What we might find is for a tertiary haloalkane, the intermediate is quite low because it's quite stabilized. But for a primary, it's quite high because it's not stabilized by the positive inductive effect. See here, I'm going to put positive inductive effects in mini, just because I said I would try not to.
Which one's low, which one's high?
The tertiary one is going to be low, intermediate, because we believe that that cation is stabilized because it has all of those other chains that are feeding into it, distributing that positive charge. Whereas the primary is not stabilized. And so what we find actually is that if we were to overlay the SN2 mechanism of this primary chloroalkane, it doesn't have an intermediate. The activation energy for just going in SN2 is lower than the activation energy for going through SN1.
so if you have less positive inductive effect, you have a higher activation energy.
Yes. So I've tried to put in blue the reaction profile for the SN2 for that primary guy. So here was the SN1 for the primary, here was the SN2, has a lower activation energy, it's going to be faster. So now some of you are thinking, does that mean both things are happening? And the answer is yes. But one will dominate over the other. So we're only going to talk about that dominant path. So we will say tertiaries will always do SN1, and we will say primaries will always do SN2. It's a little bit of a lie, but it's not big. There's some more ways to tune it that Elizabeth's already alluding to. But what I wanted to do was I wanted you guys to draw the SN2 mechanism for 2-methyl-2-chlorobutane. SN2 for 2-methyl-2-chlorobutane.
That's what we're doing now? Or that's what we did? This is what you got, right?
I didn't alphabetize well in my head. There you go, in alphabetical order, so I'm around she respects me again. I'm going for that molecule. P in the other class asked me why it was I wrote this as H3C. Margaret's saying because the two carbons have to be bonded together, so when it's on the left, I have to flip it around. Yes. I don't know, the other class lacks some common sense. Seemed like a reasonable question, seemed like something I should address. Yes, we do. So you must draw the transition state to get all 4 marks. Does anyone have K through on in their advisory class? dancing girl at the front of the line.
Yeah.
Yeah, like I didn't know for some reason that one question was blonde. So yeah.
Racist.
Oh, crazy. No, I was like, girl. Because when I think of Kate, I don't think of like brown hair. No, I can't believe you.
No, there's no positive there. There's just a negative. And now you need the next step because you do the product. Yeah. I'm gonna say you have blonde hair in this end. Like, you're the blonde in this room.
Literally, there was a time when Ray and I both had blonde hair, and instead of joining alternate with blonde, I actually had blonde hair. I had blonde hair. She didn't have blonde hair. So it's Teddy. Four of us had blonde hair. Had blonde hair. Oh, and then they were like the blonde. They didn't even know what it is. They were like the blonde. And like Miss Thomas was asking
I
them,
think
like,
it's very interesting how hard it is to refer to someone you don't know, right? Like to try to describe them.
yeah.
Like where do you go? So Joseph's former lacrosse coach was on the Korean national lacrosse team, so he's very associated with being Korean. So he went to a men's league game, and people were talking about, oh my God, that Korean on the team scored 6 goals, and he was like incensed that he wasn't referred to by the color of his helmet, by the sticker on his helmet, by the fact that he was like an amazing player, but it was down to your Korean. And so it's like, I don't know, like hair color seems like it's pretty chill. Like, oh, that blonde girl, like, ooh.
I mean, I don't know. Actually, I know I read it. My vision was like not good, but then
Okay.
I found it. I don't really care. If someone says like, oh, that Asian.
This carbon's gonna have essentially all carbons around it.
Yes.
And wouldn't it be not ideal to use?
Yes, that's gonna be a point. Why I made it C2H5?
Yeah.
I don't know. So that was hard, right? So I made it small.
I thought there was like a specific.
No. Just trying to make it cute. Show you different ways of showing it. I'll be there in a second, Audrey. Yes. Yes. Yeah. Terrible.
Wait, it's
Absolutely.
Yeah, we could do it the accent too.
Okay, I like the transition state, but you didn't show me chlorine leaving the hydroxide coming. Two arrows. That's all the way to the carbon, not to the bottom.
And then this has to go.
Don't.
All the way
Do you remember all of them? They have to go back.
to chlorine.
And then this is the
Yeah. Make sure that this line goes low, not
I just wrote it down.
Okay, good.
typing at the same time.
The carbon's directly.
Transitioning state.
I think yours is good. Yes.
I just wrote it really. Yeah, no, it's right. I just wrote it backwards.
All of last year's
That's the moral. You're right, it matters.
Oh, he's amazing.
Okay, you have too many minus signs. So there's only.
Oh, wait, that
dear.
shouldn't be
Here, you're in charge of that. I'm sorry.
It's okay.
So this is 1 minus. This doesn't have a minus. Right? This is just a neutral molecule.
Okay, because it's bonded.
And so the hydroxide comes into that carbon, the chlorine leaves. There's no positive, there's a partial positive and a partial
So I did
negative.
a S.
That's what's wrong, right? You need the partial.
Is this
How do you write
still,
partial?
It's like the,
Yeah.
Oh.
so it's still a,
Good luck.
I actually got it right.
Say good luck. Just, isn't that what you say? It's always good luck.
Okay.
They all seem happy.
It's
the happier class.
A sort
Yeah,
of
that'd be
polar
fine.
bond, right? And then,
And so you also need to show the chlorine leaving, so you need to have an arrow there.
oh yeah, that was what it was originally
Yes.
gonna be. But yeah.
And the arrow needs to start at the bond and go to the chlorine.
I dropped.
There you go. Yes.
The arrow stuff.
Okay,
is
and this needs one minus sign.
like
Just right there.
just a big
like
one.
Yes, just a big minus sign. It's like this is half of a minus and this is half of a minus. Neither of them own it right now. This one comes in with it, this one goes out with it, so they both have some charge. But overall, since this has a net 1, this has a net 1. And now you need the products.
Still doing the same thing.
what even?
But I thought this year was gonna change what didn't we?
Okay, so in my travels, these are some things I noticed.
We made a very inappropriate statement that was worded kind of wrong and not supposed to. Talking about the freshman retreat, I was like, how is the housing situation at the
And she was like, we're sleeping with the freshmen or something.
They're 15. Some of them
You
are
and Andre, where did you
13.
calm down?
I bet we're bunking with them, like we're staying in the same room.
Could have said nothing.
Are you serious? That's what happened when I was on the freshman retreat. The counselors bunked with them.
That's happens in most camps, the counselors bump with the little kids.
No, I promise you, not the
That's what
first
I
person
meant.
to say that. I'm not even.
I was so bad.
Okay, kids, hush.
Isn't it a house where bunking with children like a liability?
All you are still relatively young.
A counselor non-bunking with children is even bigger liability.
Like last year, the freshman retreat had the incident with the punching and the kid who wouldn't shower.
I did not know this.
There was punching.
Why do we never hear the cool
Shower.
stuff that happens with the freshman?
When's the punching at?
We only hear the boring stuff.
Okay, so all of you seem to have an arrow that went from the lone pair on the hydroxide to the carbon, not to a bond, but to the carbon proper. And you had an arrow that went from the carbon-chlorine bond to the chlorine. You then all seem to have an intermediate that showed a partial bond to OH, a partial bond to Cl, and the real bonds. And I redrew this, so that you would see it different ways, but also so that we could all see that there were 5 things around this carbon. Right, so I just tried to make them little groups. There are 5 groups around the carbon. And then I like to be extra, if you haven't noticed. I throw that one in a second time. I get no mark for it because I've already shown exactly that arrow here. And y'all drew me a product. And a few of you gave me an opportunity to say something I probably don't say enough. And that is when you draw a bond to OH, you can't bond to OH. You have to bond to O. You just have to be really careful with it. Yes, really. And so it's one of those things where if you stop being careful, like even though everyone knows you're right, you lose the ability to earn a mark. But again, you should have. You understand it.
What is the? That's scary.
Just trying to tell you some truth. So it also means that it's an excited state. It's optional, Audrey. It's just, I grew up using double dagger. Your textbook uses this, so I use both just to express my heritage. Name an intermediate? Name a transition state? Gosh, I'll be good at it tomorrow, don't worry. Transition state? No, you can't name that. Name that? How do you name it? Oh, you just want me to label it. Okay, I thought you meant like name it, like it's a chlorohydroxy. You do not. So the fact that you have put this here tells everyone in the world you know it's a transition state. So how do you feel about my transition state if you get to have feelings about molecules? Like a starfish? Looks nice? Okay, well I think it looks terrible. Sorry. It looks terrible because I have this tiny little atom in the middle of 5 big groups. And there is not enough room at the end. That's a Jesus joke if you don't get it. why sometimes I try to support it. Can I explain it? See, they're trying to have the
There's no
baby.
room at the inn, so we had to have a baby in manger.
So they had to have the baby in the manger. See, manger means to eat in French, so that's how we got the name manger. It was in the trough,
Really?
in the barn.
Oh.
Yeah, that's where we had the baby in the trough. Yum. Anywho, I don't like this transition state. It is too crowded, or we would say, because we're big kids now, there is too much steric hindrance.
You just make the carbon in the middle bit bigger.
Like nice silicon in the middle. So, if Amarachi is asked a very detailed question, it's not going to be a good question now. What mechanism do we think that this molecule, if I am totally out of ideas, would undergo and why? Okay, 1 mark. It's going to go SN2. 2 marks. It's primary. I'm going to need about 2 more marks.
Wait, what was the question? Polar?
Which mechanism does this undergo? Explain why.
Is the bond between the seeds?
3 marks.
Is it about the bond between carbon transition? Is it the polar bond?
It's the same thing. I just chose another halogen, so I was using a new molecule. But again,
That's a polar bond?
Yeah.
Okay.
it's meant to be. Too specific, not general enough. I want my other buzzword.
Inductive.
Positive and
Inductive.
inductive.
Wait, why is there not enough positive inductive effects?
There's only one carbon attached to the main carbon. to
Wait.
give it enough.
DT, say that again for the camera,
Give it
please.
enough electron density.
Say that again, please.
There's only one carbon attached to the main carbon, so there's only it won't give it enough electron density to
Okay.
stabilize it.
Okay, there's my 4 mark answer. I will try to read it to you because I was thinking about it in real time. This molecule would undergo SN2 because it is primary. Then I'm going to explain. There's less steric hindrance, so SN2 is favored because it can form that 5-member transition state because there are lots of hydrogens. There is not enough positive inductive effect to stabilize the carbocation for SN1 because it's still primary and there's 2 hydrogens. Those of you who did GCSE, come on, Audrey. GCSE. GCSE, pardonnez-moi, might be familiar with the fact that if you explain why it does something that sometimes without telling you the question implies, you also have to say why it doesn't do the other thing. So I never would have gotten the 4th mark on this if I had not familiarized myself with IB nonsense. I agree with the number of marks argument, but just remind yourself that if you're explaining why it does one, you need to explain why it doesn't do the other.
So SN1 will be like 3' alkane or yellow alkanes, and that's because the stability. Is that
It's because of what?
the stability?
The stability of the carbocation by the positive inductive effect.
And then SN2 will be 1' yellow alkanes because of the steric hindrance or less steric hindrance.
Right.
And the positive.
And no positive inductive effect to stabilize it. So the only thing you didn't say is that the tertiary guy will not do SN2 because there's too much steric hindrance.
Tertiary yellow alkane.
The tertiary haloalkane, or you were calling him 3', will not undergo SN2 because there is too much steric hindrance. So you correctly explained that you stabilized the carbocation. You just didn't say the counter argument. So we look at the carbon that's bonded to the iodine and we count how many carbons are directly attached to that carbon.
So we want less steric hindrance, but we want more positive.
Right, because hindrance is bad, right? Like, do you hear the negative connotation in hindrance?
So what happens when there's too much, like, steric hindrance on that one?
It just doesn't undergo this reaction. It makes the activation energy too high.
So this doesn't undergo that reaction?
No, it's just too, so this is SN2 for a tertiary.
So if it were to ask which mechanism would that undergo, you would write
I would write down, those are my 4 marks. So I gave you the answer. This is the overarching reason, but now I'm explaining how that structural piece, the fact that it's primary, is gonna favor one over the other. Amarachi,
So sorry to clarify, SN2 won't be prime because of the steric hindrance.
yes. And won't is probably a strong word. Like in IB chemistry, won't is fine, but if you go to college and study more organic chemistry, you might have some different honest experiences. Right, you can wait till then. So what do you think a secondary guy does? He does both. SN1 is a little bit faster, so it's probably a little bit better, so it probably does a higher percentage of SN1 to SN2. But it can do both. And so what do you think your quiz question is gonna be? Right, I'm gonna choose some rando secondary haloalkane and be like, draw me both structures. Right? I mean,
It does SN1 in water with SN2 in acetone.
I have often given a reaction mechanism quiz. I don't know what I'm gonna do. I don't know.
We have
Yes, carbon cup. Yes.
SN1 would be in water.
Okay, so
SN2 is more acetone.
another way that you can shift preference between SN1 and SN2 is not by changing the structure of the molecule, but it's by changing the solvent system. So I told you my favorite solvent system is aqueous, warm aqueous sodium hydroxide. That's just my favorite, so if someone asks me like, what am I gonna use, that's what I'm gonna use. For both SN1 and SN2, we need to use a polar solvent. What does polar mean? That's right, we have an unequal distribution of charge. So I'm not gonna use hexane, because that would be silly. It's not polar. And you can see that I have a charged compound here. I have something with a charge here. Like they're not gonna feel really good in a non-polar environment. So I'm always gonna use something polar because I seem to have some polar molecules that I'm putting in them. And so like likes like. We are going to use a polar solvent. But within polar solvents, we have protic and aprotic varieties. Exhaustive list, it's just a list. What is the difference between something that is protic and something that is aprotic?
Has a hydrogen ion or something.
The top 3 molecules I chose carefully because the hydrogen is directly bonded to an NO or F, meaning that all 3 of those molecules and many more are capable of hydrogen bonding, says Martha. Oh, guys, I realized something about the IB the other night, and I was so embarrassed for myself. You ever have those moments where you're like, I cannot believe I misunderstood that for like a long time? Whew, I had that.
Also
it says that you need to know the generalized formulas for all of the different functional groups and classes. And so I was sitting there struggling with like CnH2n plus 1 COOH, but then I was trying to like rewrite that so it looked like it was all one. What they meant was that you need to know that a carboxylic acid is that. That's what they meant, Audrey. I did not realize that until, I mean, I've been teaching this syllabus what seems like forever. I think they just want R and then what it is. So like that is a carboxylic acid, or this is an ester.
How do you find that?
I don't know, we practiced it together, but like I realized that's what they want instead of the CnH2n plus 2.
Is it for IV?
Like it's just one of the statements in the front of 10.1 that you need to know the general formula. And so I've always interpreted it to be like the molecular formula, but now I'm interpreting it this way. It's gonna feed into chapter 11, so I promise you'll get it. It's not gonna be bad.
What does that, the one in the brackets say on the very right on SN2?
Yeah, we're just getting there. Okay, so I tried to write you the rate laws for SN1 and SN2 because we hadn't done it. And so for SN1, you guys had agreed that the rate was equal to the concentration of the haloalkane. So I'm using R to mean the alkyl chain that's bonded to a chlorine. So R means the rest of the molecule. Kind of. And so that just represents some haloalkane. SN2, on the other hand, you might recall was a one-step reaction.
So like, where should the R's it's like the rest of any other chain.
Yes, it's just a generic term for a haloalkane. So you could write the word haloalkane there if you wanted, but like you'll see this, and that's why I was sharing my story about how I think you're supposed to know it, but I didn't teach it to you because I didn't know that's what you're supposed to know when I read that statement for the past 6 years. Haha. I teach it in chapter 11. I just didn't know that's what they meant. We'll get there. Okay, so in SN2, the hydroxide came in and attacked this carbon as this carbon gave up the chlorine. So what are the reactants in an SN2 singular step? The haloalkane, which I called RCl, and the nucleophile, which in this case is hydroxide, but I called it NU for nucleophile. I put the lone pair on it, so you saw it was a nucleophile, and I threw a negative charge on it, so it really looked like a nucleophile, like that's the best nucleophile ever. So SN2 is bimolecular or second order overall, SN1 is unimolecular or first order overall. And we're looking at these solvents and we divided them into two classes, the protic and the aprotic. And what I notice is the difference between SN1 and SN2 is that one of them actually depends on how much nucleophile is present, and the other one does not. In the presence of a protic solvent, like water, can you imagine that that hydroxide is going to be completely hydrogen bonded to every water in the system? Can you just see the hydroxide is capable of being hydrogen bonded to? So what's going to happen to that nucleophile is that it is going to be completely encapsulated in solvent. So how effective is it going to be at running in to the chloroalkane? Not. So what we find is that in the presence of a protic solvent, like water, methanol, or ammonia, SN2 goes slow. The nucleophile can't attack. It's bound up in solvent. Meanwhile, that same hydrogen bonding solvent actually really digs this carbocation intermediate. Having the ability to hydrogen bond further lowers the energy of this intermediate. So not only does it slow down SN2, but here also we find that it's a good thing. It speeds up, it lowers the activation energy of SN1. So a protic solvent is favored for SN1 because it stabilizes the carbocation intermediates. a protic solvent will not bind up the nucleophile and is less effective at stabilizing the carbocation intermediate. We choose that for SN2. So if my girl Elizabeth decides for her IA that she wants to look at the effect of solvent proticity on SN1 and SN2 mechanisms, you can imagine that you're going to take a quantitative variable like how much acetone do I have per water. So I have 10 parts acetone, no parts water. I have 10 parts water, no parts acetone. So it's quantitative in between those two measurements. And my expectation is that the reaction will go SN2 if it's all acetone, SN1 if it's all water, and I'll watch it do different things in between. It's reasonable. Are the products different for SN1 and SN2? Not at this time in your life. Your life might change, but at this time in your life, we're going to get the same numbers. It's just about the pathway that we're using to get there. We're going to be able to tune the relative activation energies by changing what solvent system we're in. If I have more time, I have one more idea. The overall reaction here has been a haloalkane and a nucleophile, like hydroxide, reacting together to make an alcohol and chloride. Fair? So I was curious how it might be different if I use fluorine, chlorine, bromine, or iodine. Which one do you think would be best and which one do you think would be worst at doing this? So there are two things that you get to do. One thing you get to do is you get to give a negative charge to a halogen. Do you remember the process of making a halide? Like where would I look in the data booklet for like an energy associated with making that minus? It's in your data booklet too.
Everybody needs it. I just forget the page.
When you're adding an electron, Audrey, what do we call it? So I would look up the electron affinity. I think it's in table 8, but who knows? I'm taking a neutral chlorine and I'm turning it into chloride. So I think this has something to do with how much chlorine wants a minus charge. So I think like the goodness of the leaving group should have something to do with electron affinity. And you might think that fluorine wants it most, fluorine is the best at becoming fluoride, and iodine is the worst at becoming iodide. Is that a reasonable periodic trend there? We say this is really small, and so since it's so small, that electron comes super close to the nucleus. We talk about Coulomb's law, so the denominator is the distance between the two charges with the lower distance because you're in the second shell instead of the second, third, fourth, fifth shell. It's a better thing. But the other thing we have to do is we have to break this bond. And this is a carbon, fluorine, chlorine, bromine, or iodine bond. Which one of these is going to be the easiest to break? There's the most size mismatch there. And so it is in fact the weakest bond. Of course you have a data booklet, right? So it's not like you need to memorize that, but you did a fantastic job. So from my point of view, breaking the fluorine bond is very hard, so that's very bad, but making the fluoride ion is very good. And on the other side, breaking the carbon iodine bond, very easy, that's a goodie, but forming iodide, it just ain't all it's cracked up to be. It just doesn't want it enough. So we have competing effects, so there is no way on earth a DT could predict which one of these is right. Do you agree? Like there is no way that you guys can look at this and decide for yourselves which one is faster. There are two competing effects. The answer is iodine. There is no way for you to solve that problem. You do the experiment. Want to know how you do the experiment? Yes,
Iodine is the fastest in breaking and making.
So if you have a series of like fluoroethane, chloroethane, bromoethane, iodoethane, the iodoethane will react fastest with hydroxide. The most common way to try to do this is to add silver ions. You do that in the form of silver nitrate. Audrey, because she's cultured, knows some rules about precipitation, and she knows that there are only 3 things that make solids with halogens: lead, silver, and mercury 1. Hg2Cl2, mercurous ion. Woo. Woo. In the presence of silver cation ions, we are going to make a precipitate like silver chloride or silver iodide. And these precipitates go from like a pretty pure white into a kind of creamy yellow. But you can just watch the formation of cloudiness and you'll see that this one becomes cloudy before that one. I'm like 90% sure that if you have the blue Oxford book, that's the one I think Brecken might rock, there's a picture of this reaction going down. Like cloudy. Cloudy. So what's the takeaway? This is like another like random qualitative chemistry fact you're supposed to know, that silver and a halogen make a solid. Cloudy. Cloudy. If any, I don't think any of you are looking at using lead in your IAs, but like one of the dumb mistakes people make if they're using lead ions in their IAs, that they use tap water. There's enough chlorine and fluorine in our tap water that you make lead chloride and lead fluoride, so you precipitate out the lead. You have to be like rigorously sure that everything was made with distilled water if you have lead ions. Very important. Yep. The best is that fluorine most wants that minus charge. It has a really big or really negative, I guess, electron affinity, whereas iodine has a much more modest electron affinity because it's a much larger ion. So, if we were trying to predict which of these reactions was the most favorable, I think a lot of us would predict that fluoride is more likely to be made than iodide. At the same time, if we're looking over here, we predicted that the I bond would be the easier one to break. And so since we have this competing thing, like we just have to reveal the answer to each other. We have to do the experiment. And the experiment says iodine. You feel like at all confident with this?
So like in the experiment, like it just shows that like
Yeah.
so the experiment just
The iodine is made faster. The silver iodide precipitates faster. It gets cloudy first.
Like substantially faster.
Noticeably faster. I don't know. I know that's what you're saying.
Scientifically faster.
It is something that one can observe. I don't remember.
Take it easy. It just went on. Come on, you can feel the side that you can see yourself.
That's me.
Do social media.
The whole day or just this last thing?
24 hours.
The rate of haloalkanes undergoing nucleophilic substitution by halogen. How would you classify it, Karthika?